So, what is an empirical formula? Well, very simply, it's the lowest whole number ratio of atoms in a compound. For instance, if I had H2O, this tells me for every two hydrogen atoms, there's one oxygen atom. And you can't get any lower than a 2 to 1 whole number ratio. Here is the molecular formula for propane. And it too is also an empirical formula because there is no lower ratio with whole numbers than 3 to 8. If I tried dividing either one of these to get a smaller ratio, I might get 1.5 to 4, but that's not a whole ratio. If I divide both of them by 3, I'd get 1 to 2.67, but that's not a whole number ratio. And then we have compounds like glucose, C6H12O6. And this molecular formula is not an empirical ratio, unlike these other two, because I can get a smaller whole number ratio than 6 to 12 to 6. These are each divisible by 2, so I can write as an empirical formula for glucose CH2O, a 1 to 2 to 1 ratio. So yes, an empirical formula is very important in determining what a substance is, being able to find these lowest whole number ratios. And so we have to know how to do that. And you don't have to be a mathematical genius to know how to find a lowest whole number ratio. As a matter of fact, you can do it by trial and error if you follow these simple steps that I've outlined up here. And I will follow these steps on an example so that we can demonstrate how it's done. For instance, if I had this ratio of things, I had 2.39 of something called A to 7.17 of something called B to 4.78 of something called C. Clearly, these are not whole numbers, but I'd like to know the lowest whole number ratio between A, B, and C. Well, my first step is determine which of these values is smallest. Cha-ching! 2.38 is smaller than either 7.17 or 4.78. Then see if each of the other values, and we're referring not to the smallest one, but the other values, is divisible by the smallest number, giving me a whole number. What do I mean? Well, if I divide this by 2.39, I get 3. And if I divide the second value here by 2.39, I get 2. And of course, if I divide 2.39 by 2.39, I get a 1. So this seemingly obscure ratio of 2.39 to 7.17 to 4.78 is really a whole number ratio of 1 to 3 to 2. And the empirical formula would be A, B3, C2. Well, I only needed the first two steps here because in step B, everything was divisible by the smallest whole number. But what happens when that's not the case? Take, for example, this ratio. If I find the smallest value, which is 0.316, and I divide the other values by 0.316, pen's having difficulty today. Well, yes, I do get a whole number in this case of 2, but if I divide this by 0.316, I get nowhere near a whole number. I get 1.5. And remember, we'd like these numbers to be within a tenth of a whole number. And 1.5 is not within a tenth of either 1 or 2. So it's not the lowest whole number ratio. So I'm going to eliminate these and see what the third step would be if this doesn't work. So I cut up here, and it says, if not, namely they're not divisible, take half of the smallest value and see if the other values are divisible by that half, that quotient that you get. So let's try that. If I take half of the smallest value, I get 0.158. Now I'm going to see if these other values are divisible by this quotient, 0.158. When I divide 0.632 by 0.158, I get exactly 4. And when I divide 0.474 by 0.158, I get exactly 3. And don't forget, if I divide 0.316 by 0.158, I get 2. In other words, this ratio isn't a 1 to something ratio like the first example. It's actually a 2 to 4 to 3 ratio. And this would be x2, y4, z3 as an empirical formula. Now, let's say that doesn't work. Let's say I did not get whole numbers when I took half of the smallest number. Well, then the last rule says, if not, take a third of the smallest value. So I would have divided this by 3 and gotten a quotient and seen if the other things were divisible by that quotient. If that didn't work, I would have taken the smallest number and divided by 4. And if that quotient was evenly divisible, I would have had a 4 to something ratio. And you go on until you finally get an even divisible ratio. Rarely do you have to go past 5 or 6 as the lowest number in the whole number ratio. So that's what we're doing. So how does this apply to chemical problem solving? Well, let's check this out. We have now, let me get a pen. We have a student measuring a 5-gram sample of an unknown hydrate of iron 3 chloride. In other words, we have FeCl3 and then an XH2O. We don't know what goes in front of that water, but we have some kind of ratio of iron 3 chloride to water. And after dehydrating this 5-gram sample, getting rid of the water, we have 2.649 grams of the anhydrate. So yes, we have 2.649 grams of iron 3 chloride because that's what the anhydrate portion is. And of course, I can use the initial mass before dehydrating and the final mass after dehydrating to figure out what portion of the original mass was water. 2.351 grams were water. So yes, I have a nice mass ratio here of iron 3 chloride to water. But of course, that doesn't really tell me the ratio of numbers of things. The example I like to use is if behind door number 1 you had 100 kilograms of basketballs, and behind door number 2 you had 100 kilograms of marbles, you wouldn't say that you had equal numbers of basketballs and marbles, because basketballs are far bigger than marbles are. And so the same mass would mean you'd have fewer of the basketballs than the marbles. It's not a 1-to-1 ratio. Mass ratios are deceiving for objects that have different masses. They don't tell you how many of each. So I'm not going to say this is about a 1-to-1 ratio, because these are masses. And a formula unit of iron 3 chloride is much bigger than a water molecule. So instead of using mass ratios to get my empirical formula, my lowest whole number ratio, I'm going to use moles, because moles are actual numbers of things. They're very large numbers of things, 6.02 times 10 to the 23rd of something, but they are numbers. So yes, 1 mole of iron 3 chloride is equivalent to its gram formula mass, 162.3 grams of iron 3 chloride, meaning that in the sample there were actually 0.0163 moles of iron 3 chloride. On the other hand, in that same sample, if 1 mole of water molecules is 18 grams, the gram formula mass of H2O, it means that same sample contained 0.131 moles of water. Now, since these are both moles, moles represent actual numbers of things. So this is how many iron 3 chloride formula units we had, and this is how many water molecules we had. And all I have to do is get a lowest whole number ratio. So, to find the lowest whole number ratio, I follow the procedure that I outlined above, namely, identify the smallest value. That would be 0.01, smaller than 0.1. And first try and see if the other number is divisible by the smallest number. And when I divide 0.131 by 0.0163, I get 8.02. And I say that anything within a tenth of a whole number is good. So yes, this ratio is actually a 1 to 8 ratio. For every 1 formula unit of iron 3 chloride, we had 8 formula units or molecules of water. So now I can take my eraser, I can erase that puppy right there, and I can throw in with my pen an 8. And the compound that I was actually measuring here was iron 3 chloride octahydrate. As another example, we have an unknown compound that's containing oxygen and hydrogen, and we're told that it is 88.9% by mass oxygen, and we can assume therefore that the other 11.1% by mass is hydrogen. Now, since percents by mass do not change depending on sample size, but we're going to need masses from which to get a ratio of moles so we know how many of each thing we have, I can pick any sample size I want to. I mean, I could pick 1 gram and figure out what 88.9% of 1 gram is and what 11.1% of 1 gram is, and use those masses to get moles of each atom. But it's far more convenient, since these are percentages, if I simply assume that I analyzed 100 grams of the substance. Because if I had analyzed 100 grams and 88.9% of it was oxygen, it means 88.9 of those grams are oxygen, and the other 11.1%, or 11.1 grams out of 100, is hydrogen. And again, I can't emphasize enough that mass ratios are deceptive. This is suggesting an 8 to 1 ratio of oxygen to hydrogen in this compound. But that's only because oxygen atoms are so much bigger than hydrogen atoms. And no, probably it is not an 8 to 1 ratio, but I can find out actually how many of each atom I have, because I know that 1 mole of oxygen atoms are the gram formula mass of oxygen, 16 grams. And I also know that 1 mole of hydrogen atoms is 1 gram of hydrogen atoms. And that when I divide this out, I get 5.55 moles of oxygen in a 100 gram sample and 11.1 moles of hydrogen. And contrary to what the mass ratio suggested, this suggests I have far more hydrogen atoms than oxygen atoms, because moles represent actual numbers of things. And in fact, if I take the smallest value and divide it into the larger value, I get exactly a 1 to 2 ratio. And this magic substance is water, dihydrogen monoxide. As a final example, if we have a 5 gram sample of an unknown compound, and it contains 1.296 grams of nitrogen, and the rest is oxygen, well, given the difference, I can and therefore assume the rest being 3.704 grams is oxygen. And again, this looks like about a 1 to 3 ratio of masses, but nitrogen atoms and oxygen atoms are different sizes, so this is not a ratio of the numbers of atoms. Instead, once again, I need a molar ratio, a ratio of moles. And since 1 mole nitrogen is 14.0 grams nitrogen, 1 mole of oxygen is 16.0 grams of oxygen, it means our actual ratio is 0.0926 moles N to 0.232 moles of O. And if I take the smallest value and divide it into the next value, I get nowhere near a whole number ratio. So then I would, by trial and error, take half of this value, or roughly 0.0458. And if I divide the moles of oxygen by 0.0458, I get almost exactly 5. And if I divide 0.0926 by 0.0458, I of course get 2, because after